Welcome to our first case study. I am Sophie and I'm a PhD student at the Institute for Neurocomputation. In this talk, we are going to investigate how dynamic field models can account for experimental data. There are various DFT models inspired by psychological results, for instance by the well-known Piaget A0B task. Today, we use the example of a new motor habituation task to show you how we set up our models corresponding to an experiment, how we stimulate it, and how we fit our models to the experimental results. But before we can do that, let me first give you some background on habituation and sensitization. They are the simplest form of learning observed in humans and animals as well. In habituation, responses to a stimulus weaken across repetitions. For instance, if you're touching a snail's antennas, it will probably shrink and hide in its house. But after some repetition, you wouldn't bother the snail anymore, and this is habituation. Habituation is specific to the stimulus, meaning that when you now touch it somewhere else, the response to hide may be reinstated and you would get dishabituation. In sensitization, however, responses are easier to elicit across repetitions. But why are we interested in that? Habituation is a tool for studying infant cognition. So you could present a visual or auditory stimulus repeatedly and measure the infant's response as looking time or heartbeat. And then you could measure the amount of dishabituation when you present a new stimulus and infer about discrimination or recognition abilities of the infants. In our experiment, a box with the lever was presented to toddlers and they could play with it moving the lever. And the box could be pushed towards the toddlers on a track to initiate movements and pulled back to stop it. The box emitted music when the lever was slid to make the movement more exciting, and on the other hand, the environment was pretty boring. Before we take a look at the results, let me give you some insights into the experimental procedure. So we had an habituation phase where the box was pushed repeatedly to the toddlers for 15 seconds and then pulled back for an intertrial period of time. During the trials, movement time, path, and looking time were recorded live. The habituation phase ended after a maximum of 15 trials, or once a criterion is reached, which is the sum of movement time of the last 3 trials is less than 50% of the first 3 trials. After that, the test phase started, and for this, the box was rotated by 90 degrees for 2 trials. Now we have a new movement direction, and the question is, do we observe dishabituation? After that, the box was rotated back to its initial orientation for additional trials. And now the question is there still habituation? You can see the resulting movement times for 2 age groups. We had 12 and 15-month-old toddlers, and 2 habituation conditions, which is basically starting with either the horizontal or vertical movement. You can see the first and last 3 habituation trials and the test trials. T1 and T2 is in the new movement direction, and T3 and T4 in the old movement direction. So what do we have here? We have a significant habituation in the last habituation trial, and we have dishabituation in the test trials when the new movement direction is introduced, and then movement times are increased. And we have the Spencer-Thompson dishabituation when the old stimulus is again presented, and movement time now is higher than at the end of the habituation phase. So this is a kind of sensitization because the response is stronger now than before. Okay, so let us set up a dynamic field model accounting for these results of the motor habituation experiment. Where do we start? First, we postulate dimensions, and here we have an abstract one, it's the movement direction. Why we would do that? Because the movement direction is the only dimension that is varying in the experiment. So we have a one-dimensional dynamic field and no input so far, so the field is at its negative resting level. We have no connection to the motor surface in this model, so we do not model the movements explicitly. This is why we would call it a movement planning field. Also, we are only interested in horizontal and vertical movement direction. So let us evaluate the field at these two sites. Now we need some input to get something on in our field. And this is perceptual input, but it has to be on the dimension of movement direction because otherwise we couldn't apply it to our field. Think about it as already processed in some kind. The box is possible to reach, the music is playing, and this leads to a movement in either vertical or horizontal direction. And we have no explicit connection to the perceptual surface as well. The inputs are modeled by Gaussian functions that are applied to the movement directions, and we will have a detailed look at the stimulus inputs later on. Now, when the stimulus is strong enough, activation in the field goes through detection instability, modeling the decision to move. So far so good, but there's no habituation in this model because the movement planning field would simply be suprathreshold when the stimulus input is strong enough. Let us introduce a second layer of field that receives input from the movement planning field. And the movement planning field itself still receives the perceptual input. For habituation, the second layer field now must inhibit the movement field, so it contains inhibitory interneurons. It lowers the activation in the movement planning field, and it might even go through the reverse detection instability, which would model the decision to stop a movement. This setup still only depends on the current stimulus, and responses do not depend on the history of decisions. But this is what we would need for habituation. So we would like to have some kind of learning, some kind of change of behavior in our model. And this is where the memory trace comes into play. You learned about it in the tutorial. The memory traces keeps track of the history of suprathreshold activation in the field, which are decisions to move in our case. Memory traces are not simply a record of the past, they actually influence the behavior. And they could lead to diminishing responses or they could intensify responses, which is actually habituation and sensitization. The memory traces doing that by changing the dynamics of the fields, by changing the fixed points of the dynamics. Okay, that sounds great. Let us add memory traces to our architecture. So we have one memory trace for the movement planning field and one memory trace for the habituation field. Now, with activation in the fields, the memory traces grow and provide input back to the fields, supporting the movement directions. Now, in the first case, we get sensitization because the response in the movement planning field is easier to elicit. In the second case, we get habituation due to the inhibitory layer because responses now are inhibited over a longer period of time. And this actually is our full model. Let us take a closer look at the different perceptual stimuli now to see how experimental conditions can be implemented. We have three different inputs. At first, a task input, indicating the orientation of the box and affording a horizontal or vertical movement. It is applied repeatedly in the simulation at either the H or V side for 15 seconds and then removed for the intertrial period. Once the field now gets suprathreshold, we add a second input, which is the reward input. It corresponds to the music and supporting the current movement. It is added once the movement planning field is suprathreshold, and this corresponds to the toddlers moving the lever. so it stabilizes the decisions to move. However, sometimes toddlers wouldn't move the lever even when the box is in their range in the experiment. And then parents draw attention to the box or even put the toddler's hands on the handle. In our simulation, we added a second input to the task input when the field doesn't go through detection and stability within 5 seconds of the simulation. So once the field goes through the detection and stability by the help of the attention input, it is removed and the reward input is added. So when you think about it, with these 3 inputs and the conditions when they are applied, we control the whole experimental setting. The model without field components, the varying inputs, and the experimental conditions is implemented in Cosivina, which is a MATLAB framework for building dynamic field architectures. You can find it on our website, and with the help of some examples, you can easily build your own architectures there. Before we jump into fitting the results and tuning some parameters, I want to show you a video on our simulation so that you can get a feeling of what we are dealing with here. Okay, now what can we see here? On the left-hand side, we have the movement planning field and its memory trace, where the time is on the x-axis and the movement direction on the y-axis. And on the right-hand side, we can see cuts through these surfaces at the horizontal and vertical movement direction we are interested in. On the right-hand side, we are not only seeing the movement planning field in blue, but also the arbitration field in red and the inputs in green. And we already have 2 trials here. We started at the horizontal movement direction, where we have the task input here and the attention and rewarding input on top of it. We can see that the movement planning field is super threshold in this trial, so the lever is probably moving. And you can see how the arbitration field nicely follows the activation of the movement planning field here. Let me play the video so we can follow the time evolution. And what you can see here in this trial is that this model is already fitted. So we have a shorter period of superthreshold activation in this trial here, which is a hint to habituation, and the criterion will probably met in the next trials. And here's it, we switch to the opposite movement direction for the test trials. What we can see here is that movement time is reinstated, and also when you take a look at the memory trace, that it goes down here because we do not have any input at the horizontal movement direction, but instead it builds at the vertical movement direction. And now we simply go back to the opposite movement direction for the additional trials. Okay, now we are prepared to go into fitting of the results. A short reminder, we want to adapt our model so that it accounts for the experimental results you can see here. At first, we need an equivalent to moving time so that we can compare our results to the experimental results. Let us define it as the simulation time per trial during which the activation is super threshold, meaning that the lever could be moved. And we simply count these time steps per trial in the simulation. So with this translation, let us take a short look at the equations we implemented in our simulation. We have the movement planning field U and the habituation field V, and with their dynamics. We have no excitation in the arbitration field, and all inhibition of the movement planning field comes from the arbitration field. Both fields get input from the memory traces, and the movement planning field provides input to the habituation field, and the habituation field inhibits the movement planning field. And these are all 3 parameters. We have timescales, we have the resting level, we have inputs, which are only applied to the movement planning field, and we have the kernel. And the kernel have a fixed geometry, but we can vary 3 parameters here, the width and a global component. And because this is not enough, we also have parameters in the memory traces. And here only the timescales differ for the build-up and the decay of the memory traces. So these are a lot of free parameters, but also we have a lot of constraints given by the experimental conditions. And I want to show you some of them. We have that the timescales of the memory traces are slower than the timescales of the field, obviously. We have at second that the decay of the habituation memory trace is faster than the decay of the sensitization memory trace. And this is because the sensitization memory trace should predominate in the second test phase so that we can get to the Spencer-Thompson dishabituation. We have full habituation after some trials. That means that toddlers would refuse to move the lever without being influenced by their parents. And so, we know that inhibition of the movement planning field must be stronger than all excitatory inputs to it. We have that the coupling from the movement field to the habituation field must be strong enough to cause superthreshold activation. So otherwise, there would be no habituation. And this gives us that the coupling must be stronger than the resting level of the habituation field. Next, the task input in addition to the attention input, or the task input plus the input from the sensitization memory trace must be strong enough to cause superthreshold activation. So obviously otherwise there would be no movement. But toddlers would not move the lever in a new environment without being encouraged by their parents, which is the attention input. And after that, they only move the lever because they know that music plays and they repeat the movement due to sensitization. So in our setup, the task input alone is not sufficient to cause the superthreshold activation in the movement planning field, meaning that there would be no movement only because of the box. Then we have that without the music, toddlers would stop to move the lever because the movement would be simply boring without some exciting music playing. And there are even more constraints, but let us now take a look at the results. These are the average movement times from the simulation, and we added noise to the fields. I didn't show you that on the previous slides. And because of this noise, we averaged over 50 simulations, and we have the standard deviation in gray here. And what do we have? We have a habituation in the last habituation trial, dishabituation in the first test trials when the new movement direction is introduced, and even the Spencer-Thompson dishabituation when we have the old stimulus again. And this is exactly like the experimental results we wanted to model. Okay, so that's great. Let us summarize what we did here. We had the motor habituation experiment where we observed habituation, dishabituation, and the Spencer-Thompson dishabituation. And we set up a DFT model by first postulating the relevant dimensions and then adding perceptual input, which can be applied to the field because it has the same dimensions. We have the interpretation of activation peaks as movement plans and decisions to move. We added the second layer of inhibitory neurons for habituation. And then we added the memory traces for actual learning and actual change of behavior. We translated this back to the experimental measures as moving time in the simulation. And then we fitted parameters using a lot of experimental constraints. And finally, we compared the results of the simulation to the experimental results. And by this, we found that we can model dynamic fields unifying habituation and sensitization. And this actually accounts for the data we found in the motor habituation experiment. So I want to thank you for your attention. Here are some references you might be interested in when you enjoyed the talk. And I am looking forward to questions in our discussion.